Hello, everyone. Welcome to another episode of Q&A about science and technology for kids and others. And I see we have a whole bunch of questions saved up here. Let me go to these. There's one from Anon that asks, what is muography? It's a somewhat new term, and it all has to do with muons and the analog of X-raying things, but with muons. So let's start off by talking about X-rays. When you look at your hand, you basically just see the skin on the surface of your hand. Light doesn't get very far into your hand until it bounces back to you. Actually, skin is kind of a complicated material because light does go a little tiny ways into skin. That's been why it's so difficult to kind of do computer graphics renderings of skin. But in any case, basically, ordinary light just gets reflected off your hand, or what you see is reflected off. Other light is just absorbed. The photons just go into your hand and they kind of disappear into atoms and they get absorbed by the atoms. Okay, but light you can think of as a stream of photons. Each photon has a certain energy. And as you crank up the energy, you go from having light, photons of light, to ultraviolet, to and then to X-rays. So X-rays are like light, a stream of photons, but each photon has a higher energy. And photons, X-ray photons, have enough energy that they can blast their way through material like your hand. And so many of X-ray photons will go all the way through your hand. Now, it turns out that whether you can get through or not depends on what the chance when an X-ray photon encounters an atom in your hand, is it going to just be absorbed by that atom, or is it going to kind of keep going on through? And it turns out the rate at which photons are absorbed by atoms increases with the size of the nucleus of the atom. So in the different chemical elements, hydrogen, helium, lithium, beryllium, boron, etc., all 120-ish of them, the number, that number, hydrogen is 1, helium is 2, etc., that number is telling you the number of protons in the nucleus of the atoms for that kind of element. And it turns out that the chance for an X-ray to be absorbed increases like the square of the atomic number, the number of protons in a nucleus. And so what does that mean? Well, it means if in your hand, for example, there's a bunch of water, H2O, hydrogen and oxygen, there's a bunch of carbon, there's a bunch of other elements, but there's also calcium in your bones. And calcium has a higher atomic number. I should remember what its atomic number is. I think I'd have to recite the periodic table to work it out. But it has a higher atomic number. And so when X-rays hit atoms of calcium in your hand, there's a much higher chance that the X-ray photons are absorbed in the calcium than there is that they get absorbed in the hydrogen or the oxygen or whatever else. So that means as the photons are going through your hand, there'll be places where you get to bones that have a bunch of calcium in them, where the photons get absorbed, and other places where they don't hit the atoms like calcium and they go right through. So what that means is when you make an X-ray picture of your hand, the places where the X-rays coming through hit calcium, hit bones, the photons don't get through, and other places they do get through. And the way this was set up in the early days of X-rays, it was where the film was exposed, it went black, and where it wasn't exposed, it stayed white. And so that means, conveniently, the bones wind up looking white on an X-ray because that's where the X-rays didn't get through and didn't have a chance to expose the film. So X-rays have this feature that they get stopped more by heavy elements than by light elements, and but they manage to kind of blast their way through a certain amount of material, much more so than light does. Some substances like glass, for example, silicon oxide, are transparent to ordinary visible light, and so you can see through the window, so to speak, because it so happens that the energy of photons that corresponds to visible light makes it through the material that corresponds to glass without getting scattered. Now, normally, for any given type of atom, there are particular frequencies of photons that the atom kind of likes to absorb. The reason that happens is that in an atom there are electrons, and actually this is a slightly more complicated explanation, because when essentially the higher energy the photon, the smaller scale the features that photon is sensitive to are. So, for example, photons are radio photons, the photons that you can think of being making up radio waves. Those are big blobby photons, so to speak, and so they are completely insensitive to small scale things. So, for example, if you look on a microwave oven, you'll probably see that you can see into the microwave oven because there's a window in the front and there's kind of this mesh inside the window. There are holes in the mesh that you can see through, that light can get through, but that mesh, as far as the photons of radio photons that are part of the microwaves in the microwave oven, they get stopped by that mesh because they're sort of big and blobby, and they when they hit that mesh, they kind of can't go through, even though there are holes that are perfectly good enough for you to see through. So roughly, the higher the energy of the photon, the more it's sensitive to very small scale stuff. So when you have a photon of visible light, it's sensitive to things on kind of the scale of a whole atom, both the nucleus and the electrons that are 100,000 times, the nucleus is a 1/100,000th of the size of the whole atom in linear dimensions. And so visible light, its photons are kind of the right size in a sense. The discussion of what exactly one means by the size of a photon is a little bit complicated, but it's kind of like that's the region over which the photon, of which you kind of don't know where the photon is. It effectively has some size, and that size is comparable for visible light to the size of atoms. And what is most important in kind of the interaction of visible light with atoms is features of the electrons in atoms, because those are the things that are sort of out at the size of which there is sensitivity. When it comes to X-rays, those have higher energy. Their photons have higher energy, and they're mostly sensitive to things that happen in the nucleus of the atom. They don't really pay attention to this bigger sort of thing of the electrons. There's a sort of empty space between the nucleus and the electrons. They're really sensitive to what happens inside the nucleus. And when you get even higher energy photons, the kinds of things you might get in a particle accelerator, you might be sensitive to details of quarks inside protons and things like this. But for X-rays, you're sensitive to kind of the whole nucleus, and this feature of, well, how many protons do you have in the nucleus? That's going to determine and neutrons, but how big is the nucleus? That's going to determine the scattering, the absorption of X-ray photons. Okay, so that's roughly how X-rays work. They are much more sensitive to heavier elements than lighter ones, but they basically for lighter elements, they'll manage to go through the kinds of things that, for example, sort of you can go through the volume of material that's in one of us humans, for example. Clearly, if you wanted to, for example, X-ray a mountain, wouldn't work very well. Although going through a hand or something, yes, the X-rays will readily do that. By the time you've got 5 feet of rock or something, the X-rays won't get through. They have a certain chance of being absorbed, even if the only things absorbing them are, let's say, carbon or something. There's still a certain chance the X-ray gets absorbed. And when you get a thicker and thicker region of material, the chances are the X-ray will have gotten absorbed before you get very far. Okay, so the question is, if you want to be able to see through rock, for example, how might you do that? It's not going to work with any form of electromagnetic radiation, any kind of thing with photons, because what are the possibilities? Well, there's radio photons. They get stopped incredibly quickly by something like rock. There's visible light. Well, we know you can't see through rock with visible light. With X-rays, you also can't, they don't go very far into rock. You can go to things like gamma rays and higher energy photons. They also don't go far in something like rock. So the question is, what does? Well, one of the things that really does well is neutrinos. Neutrinos are particles that are, well, they're almost of zero mass, and they have very few interactions. Neutrinos don't have an electric charge. An electric charge is what makes things participate in electromagnetic interactions. So things like electrons have an electric charge. They are that's, well, if you sort of wiggle an electric charge around, you will generate photons. Photons are kind of the carriers of the force associated with electromagnetism. Photons themselves don't have an electric charge, but they're generated by kind of motion of things with electric charges. They're the kind of carriers of information about where there was an electric charge, so to speak. Well, neutrinos don't interact just on the basis of things having an electric charge. They're only sensitive to so-called weak charge, which is a kind of a different kind of thing, like electric charge, but not electric charge, a kind of thing that's associated with the so-called weak interactions, which are much more obscure thing to at least us than electromagnetic interactions, things to do with electricity and magnetism and light and so on. Weak interactions, the main effect that one might be familiar with about that is radioactive beta decay. So what is radioactivity? When you have an atom with a nucleus, the radioactivity happens when the nucleus is unstable and flies apart in some way or another. There are different forms of radioactivity: alpha, beta, gamma, and spontaneous fission. Spontaneous fission maybe is easy to explain. It's what happens in some very big, heavy elements like uranium-235. 235 means that's the total number of protons and neutrons in the nucleus. Uranium-235, after a very long time, a few billion years, the nucleus is just sort of too big and globulous and just falls apart. But it takes a couple of billion years to do that, typically. Other nuclei are unstable for other reasons. So an alpha decay is a nucleus just sort of is a bit too big in some sense. And a sort of lump of nucleus that's 2 protons and 2 neutrons, it's the same thing that you would find in the nucleus of helium-4, just sort of falls off, and the nucleus then loses 2 protons, 2 neutrons. Then there's another form of radioactivity, which is beta decay. In beta decay, let me come to that in a moment. Gamma decay is just the nucleus is a bit too excited, and it emits a high energy photon, and it's kind of its protons and neutrons sort of wiggling around a bit too fast. It loses energy by emitting a high energy photon. Then the third kind, there are different kinds that have to do with emitting protons, emitting neutrons, things like this. They're a little bit less common for reasonably stable elements. But another kind is beta decay, and beta decay is what happens is this. Okay, so nucleus consists of protons and neutrons, and the nucleus is that the protons and neutrons are held together not by electrical forces, because electrical forces are such that unlike charges attract, like charges repel. So if you have a positive charge and a negative charge, they'll be pulled together by electrical forces. If you have two positive charges, they'll be pushed apart by electrical forces. But protons in the nucleus all have positive charge. Neutrons have zero charge, but protons have positive charge. So you might think, how can a nucleus possibly hang together? It's got all these protons with positive charge. It should just blow itself apart. The reason it doesn't do that, something which was first hypothesized in the 1930s, is that there is another kind of force, the so-called strong nuclear force, which holds the nucleus together, and it's different from electromagnetism. Just as electromagnetism is the result of essentially photons being bounced backwards and forwards between particles with electric charge, so the strong nuclear force, in a first approximation, is the result of a kind of particle called pions being bounced backwards and forwards between particles like protons and neutrons. So pions, they don't have a very long range. They don't go very far. Pions, unlike photons, which have zero mass, pions have a mass of about a tenth the mass of a proton, and they don't go terribly far. They only go about the distance that's the size of a nucleus. But they're kind of continually being exchanged between protons and neutrons and so on. And pions have the feature that they make different, all kinds of particles they make attract to each other. So they have this, they produce this force which holds the nucleus together. Even though electrical forces would make the nucleus fly apart, strong nuclear force holds the nucleus together. And so that's how that works. Now, in the nucleus, there are protons, there are neutrons. If you separate out just one proton on its own, which is what you get in the nucleus of the most common form of hydrogen, it's just a proton. The hydrogen atom is just a proton in the middle and an electron outside. You can have a separated proton, just have it hanging out wherever. And so far as we know, it's completely stable. The proton can just sit there for a really long time. The limit these days is about 10 to the 32 years. That's a trillion, billion years, roughly. So as far as we know, a proton just sits there, doesn't decay, just stays stable. Good thing for our universe, because that's what allows matter in our universe, means that the matter in our universe can just stay without decaying. Okay, a neutron, it's a much more marginal situation. If you could separate a neutron from the nucleus, just have a separate neutron on its own, turns out in about 15 minutes, the neutron will decay. So a separated neutron, separated from the nucleus, manages to just decay after about 15 minutes. Inside the nucleus, the neutron is kind of bound tightly enough that it kind of doesn't have the sort of energy that it needs. In order to decay, it's going to turn into other particles. And in a nucleus, the neutron is kind of bound in, and those other particles don't have that binding, prevents the neutron from being able to sort of explode into these other particles. So neutrons in a nucleus are roughly stable because they're prevented from their decay by this binding into the nucleus. Well, that doesn't work perfectly. So some nuclei, their neutrons are not bound in tightly enough, and the neutrons are still able to decay. So, for example, an example of that is tritium, the isotope hydrogen-3, the isotope of hydrogen. So isotopes are sort of variants of chemical elements which have all versions of, let's say, hydrogen have the same number of protons in their nucleus, one proton in the case of hydrogen. But there are these different variants, so-called isotopes of hydrogen, which have different numbers of neutrons in their nuclei. So ordinary hydrogen, sometimes called protium, has just that single proton in its nucleus. Then there's another kind of hydrogen called deuterium, which has a proton and one neutron in its nucleus. Deuterium is, I think, one in 10,000, I think. Hydrogen nuclei will be deuterium nuclei. Deuterium, which we see was mostly made at the beginning of the universe, in the first second or so of the existence of the universe. But deuterium is again stable. Deuterium, the nucleus is a proton and a neutron. Okay, there's another form of hydrogen called tritium, which is a proton and two neutrons, hence hydrogen 3. Okay, so tritium is not stable. Tritium, that extra neutron, is not quite tightly enough bound to prevent it from decaying. So tritium decays with a lifetime of about maybe 20 years, something like that. Notably, the amount of tritium in the world has gone down in recent years because, if you look at tables of sort of what the atomic mass of hydrogen is, which the atomic mass is determined by sort of the average mass of the nucleus, which is determined by sort of how many protons, how many neutrons are in the nucleus, because they all contribute to the mass of the nucleus. And that means when you look up the atomic mass of a material, it's often some complicated decimal. It's not sort of an integer. It's not like the atomic number, which is just that's the number of protons. It's, well, the actual mass of protons and neutrons is slightly different, but the other reason why you get sort of a complicated number for the atomic mass is it depends on the relative abundance of different isotopes. So for hydrogen, the atomic mass isn't exactly 1, it's 1 plus a bit, depending on how much deuterium is around, which has roughly atomic mass 2, and how much tritium is around, roughly atomic mass 3. And that number has changed over the last 50 years or so. And the reason is this: in the 1950s and 1960s, there were a bunch of nuclear weapons tests done, particularly in the Pacific Ocean, and those generated a bunch of tritium. And so, and that, what people could tell was that tritium spread throughout the oceans of the Earth quite quickly. And so you pick up a typical, some water somewhere, and it would have some tritium in it until the tritium decayed. And after 25 years or so, that tritium is mostly decaying. Tritium has a certain, like all radioactivity, it has a certain half-life. That means there's a certain chance that each nucleus will explode, will decay, and the half-life tells you after how much time will half of the material in your bottle of that material, or whatever it is, have decayed. And so after one half-life, you've got half as much material. After 2 half-lives, you've got a quarter as much. After 3 1/8 as much, and so on. That's the kind of exponential radioactive decay. So, okay, in any case, so the amount of tritium in the world is a bit smaller than it was. But tritium has this extra neutron, and the extra neutron is not bound tightly enough to prevent it from doing what free neutrons do, which is to decay. And what does a neutron decay into? Well, it decays into a proton, an electron, and an antineutrino. So a neutron has 0 electric charge. An electric charge is conserved, so that means that a neutron has to turn into something where it has to turn into things where the total electric charge is still 0. So a proton has a +1 electric charge, an electron has a -1 electric charge. So a proton and electron, those are good things for it to turn into. But then it turns out there are other things that are conserved different from electric charge. There are other kinds of charges that are conserved. Essentially, another kind of charge is essentially electron, a kind of a charge associated with the number of electron-like things that are there. And so electrons are an electron-like thing, but because you're producing an electron, you have to have an anti-version of that to cancel out the electron-like charge associated with the electron. And that anti-thing is an antineutrino. So antineutrino is sort of the third piece in the decay of a neutron, and that antineutrino has the feature that it has very low mass, but its only interaction, the only way it can interact is with, it interacts with electrons and quarks actually, but it interacts through this very weak interaction process. Okay, to fill in a little bit more here. So I mentioned that electromagnetic interactions are associated with photons being exchanged between things. When you have electrically charged things and you're wiggling them around, they're producing photons, and the photons are being absorbed by, well, actually, anything with electric charge produces photons, which can then be absorbed by other things with electric charge. And the kind of the analog of that for weak charge is not photons, but so-called W bosons. And W bosons were just sort of a theoretical thing for a long time. Then in the 1980s, they were actually discovered in particle accelerator experiments. A W particle has a mass of about 80 times the mass of a proton, and W particles kind of don't manage to go very far. They go a tiny distance, and but they're able to sort of have processes that involve weak charges happen. But those things are very weak, basically because W bosons can't go very far, and they involve very sort of small distances and so on. And so their typical kind of interaction strength, chance of being produced and so on is low. And that means that the rate of interactions that have to involve W bosons, so-called weak interactions, is very low. Those are the interactions that are needed to be able to like produce an electron and neutrino. And if the neutrino is ever going to interact with anything, it's got to be through those interactions with W bosons and so on. Now, tricky fact is that the weak interactions like that have the property that the higher the energy of the neutrino, the more likely an interaction is. Most kinds of interactions have the feature that the faster a particle is going, the less likely it is to interact. The sort of the smaller the effect of the sort of force associated with some exchange of a particle is, roughly. But in the case of weak interactions, it turns out the probability of interaction increases with energy, at least until you get up to energies that are comparable to the mass of the W boson. So, but in any case, for the electrons, for neutrinos, of the energy associated with beta decay, neutrons decaying into protons, electrons, antineutrinos, the interaction probability is very low. So a typical neutrino that is produced from beta decay will be able to go a long way. It'll go, neutrino will typically go all the way through the Earth. It's kind of like if you're trying to X-ray things, X-rays will get stopped. X-ray photons will get stopped after a very short distance, but neutrinos can just tool right along and go, for example, all the way through the Earth. Well, the problem with that is if you want to know, well, what's inside the Earth, why don't we just use neutrinos as the analog of X-rays to find out what's inside the Earth? Interesting idea. The problem is, just as neutrinos go all the way through the Earth, a detector of neutrinos, they'll also go all the way through your detector. And in order to detect the neutrino, you have to see it actually interact somehow. Well, there are neutrinos produced from the sun, and it was a long sort of challenge to observe neutrinos produced from the sun. The main problem is that, well, in the end, if you have detectors, sort of big volumes of material in which neutrinos can interact, and where the material is transparent enough that you can see the result, you can have, for example, the interaction of the neutrino with some atom, for example, might kick out the proton or the electron in the atom, make it go really fast. That will produce what's called Cherenkov radiation, which is a little flash of blue light, basically. And if you have a big tank of material and it's transparent enough, and you've got things that detect flashes of light, then you can just sit there and wait. And every so often, there'll be an interaction for a neutrino, and you'll get a little flash of blue light, and you'll be able to see that in this big tank of material. Problem is that if you put a big tank of material on the surface of the Earth, there'll be all kinds of cosmic rays that come mostly from the sun that get into, that produce kind of interactions that make those little flashes of blue light. The only way that you can avoid those is to bury your detector in some deep mine, but underneath miles of rock. And then most of the particles that come from cosmic rays, they'll just get absorbed by the rock. But the neutrinos, which go all the way through the Earth, will happily trundle right along and get into that tank of material that you have. And then when you see a flash of blue light, you know that must have come from a neutrino, because nothing else would have survived that deep, or at least very little would survive that deep. So anyway, it was a big challenge to detect solar neutrinos. It was eventually done. There were all kinds of details about neutrinos. But that wasn't our subject here. Our subject here was muography. And that's something where the question is, can you kind of do the analog of X-raying things like rock? And as I mentioned, neutrinos, they successfully go all the way through rock, but it's very hard to detect them. Okay, so is there something that will successfully go through some rock, for example, but still be detectable, but go through much more rock than, for example, light would go through or electrons would go through or whatever else? And the answer is yes. There are these funny things called muons, and they have lower rates of interaction, and so they can go through larger amounts of material. What is a muon? A muon is a thing that, so far as we know, is just like an electron, but about 206 times heavier. Nobody knows why muons exist. It's been sort of an unsolved problem since muons were discovered in the 1930s. Actually, there's even a third creature in that same series called the tau lepton, which is about 1,700 times, it's about 3,000 times heavier than an electron. And it's the electron, the muon, the tau lepton. These are all things that seem like they're the same kind of thing, but they have different masses. We don't know why they exist. Okay, what is a muon? What's the story of a muon? Well, electrons, so far as we know, are completely stable. And that's a little bit unsurprising. If electric charge is conserved, they are the lowest mass things with electric charge. So there's nothing that they can decay into while preserving electric charge, because to decay into something, it has to have lower mass. So a proton, if a proton was unstable, it might be able to decay into an anti-electron, which has positive charge, and neutrinos and some other things. Because there is a lower mass electrically charged object. But for electrons, it's the lowest mass electrically charged thing, and so it's probably stable, can't decay. Okay, so electrons are stable because there's no lower mass charged particle. Muons don't have that feature. Muons can in principle decay into electrons. Well, actually, muons decay also through this weak force, and muons, a muon, there are two kinds of muons, mu minus, which is kind of like directly like an electron, and mu plus, which is kind of like a positron, an anti-electron. A mu minus decays into an electron, a muon neutrino, and an anti-electron neutrino. There are different kinds of neutrinos. There are three kinds of neutrinos. They're kind of paired up with the electron, the muon, and the tau lepton. So, and actually within each kind of neutrino, there's both the neutrino and the antiparticle of that neutrino. So altogether 6. But in any case, a muon decays into an electron, a muon neutrino, and an anti-electron neutrino. And how long does it take to do that? Well, it takes its lifetime is about 2.2 microseconds, 2.2 millionths of a second. Okay, so that's actually, in some sense, a fairly long time. And one of the features of relativity is that when particles go faster, the time it takes them, time goes slower for them. And so in particular, the time, if a muon, normally when it's just sitting there, has a lifetime of 2.2 microseconds. When the muon is going really fast relative to you, the muon will seem to have a much longer lifetime. And in particular, there's a formula that says that if v is the speed that the muon is going at and c is the speed of light, the lifetime goes up like 1 over the square root of 1 minus v squared over c squared. And what does that mean? That means when the velocity of the muon is very close to the speed of light, the effective lifetime of the muon will go to infinity. Okay, when you produce a muon from some energetic particle interaction, it will typically be going quite fast, and so its effective lifetime will be a lot longer. So as I'm talking to you, there's probably one muon going through me every few seconds. Where do those muons come from? They're coming from cosmic rays. They come from the sun. The sun spews out both light and lots of protons. The protons arrive at the atmosphere of the Earth, and protons tend to interact with the particles in the air. And so chances are by the time you're at sea level, there's still a bunch of primary cosmic ray protons. If you're like in Denver, a mile high or something, there's still a bunch of primary cosmic ray protons that are hitting the ground. But by the time you're at sea level, most of those protons have interacted with some atom in the air. And so those protons have been, have turned into other things. So typically a proton interacting with a proton in an atomic nucleus or something, it'll produce a big shower of things like pions, which I mentioned before. Pions are the things that are exchanged between protons and nucleus to bind the nucleus together, but they can also exist as free particles. Pions decay as well. There's a pi plus, a pi minus, pi zero. The pi plus and pi minus decay in about 100 millionths of a second. The pi zero decays in about a million billionth of a second. So there's what do they decay into? The pi zero decays into 2 photons. Let's ignore that for a second. But the pi plus and pi minus decay into a muon and a neutrino, or an antineutrino. So protons hit the upper atmosphere of the Earth. They collide with protons. They produce showers of pions. Those pions decay in 100 millionth of a second into, or a little bit longer because the pions are going kind of fast, but they decay into muons. And the muons are the things that survive to the surface and will be going through you every few seconds if you're at sea level, for example. And those, so its proton goes to pion, pion decays to muons, then the muons will eventually decay into electrons. But it takes a while for them to, it takes that 2.2 microseconds, and increased by that relativistic factor associated with them going faster. Maybe it's worth explaining that relativistic time dilation phenomenon. It's become a lot easier to explain that phenomenon with our theory of fundamental physics that has emerged in the last few years. Essentially, you can think of it this way. When a particle, like a muon or something, exists somewhere, it is composed in our theory of little sort of atoms of space, a very large number of kind of elements that make up the structure of space. And as the muon is just sort of sitting there, it is continually restructuring itself internally. It's continually rearranging those atoms of space. So it takes a bunch of sort of computational effort for the muon to just be there and be rearranging itself as a muon, but so still be somewhere. If you want the muon to be moving as well, the muon is essentially having to recreate itself at different places in space. And that too takes computational effort. And in a sense, there's sort of a trade-off. If the muon is moving really quickly, it's spending a bunch of its computational effort recreating itself very rapidly at different places in space. And so it sort of has less computational effort that it can spend to just kind of do the things that muons do when they're not moving. And so among the things that muons do when they're not moving is they decay, but that process, that sort of clock that is determining how long it takes to decay, is going to be running more slowly because a lot of the computational effort that might have gone into essentially running that clock is instead going into the recreation of the muon at a different place in space because the muon is moving. So that's kind of the reason that there's time dilation, that sort of time effectively moves more slowly for an object that is recreating itself as moving in space. So, okay, in any case, the end result of all of this is you've got muons streaming onto the surface of the Earth from cosmic rays. Well, muons, it turns out, go much deeper into things like rock before they will typically scatter. So, okay, what's the point of all of this? You can detect muons. They have electric charge. They are detectable through all sorts of particle detection methods. Roughly, okay, how do particle detectors work? There are different kinds of particle detectors. A pretty common kind, well, a very old kind is things called Geiger counters. And what does a Geiger counter do? A Geiger counter is using the fact that you can, well, it's kind of like a microscopic lightning strike. In a lightning strike, you've kind of got it's so that there's a very high voltage across a piece of air, and when there's sort of when something goes through, you can kind of you have breakdown in the air. That very big voltage difference, it wants to just it wants to kind of have the thing in between break down and just have electrons flow from sort of low voltage to high voltage to low voltage, depending on how you set it up. And what happens in a Geiger counter is you've got essentially a very high voltage across a gas, and when a charged particle goes through the gas, it kind of the Geiger counter is sort of unstable to this breakdown happening, and when a charged particle goes through, it kind of kicks over the instability, and there's this kind of little discharge, like lightning strike, little microscopic lightning strike that happens, and it's like, okay, you can tell that happened. And if you have an actual Geiger counter, they're hooked up to loudspeakers, and you'll hear the click, 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 click. Each click is one of those little breakdown processes occurring as a particle as a particle goes through and initiates that sort of the instability. Geiger counters, another common method that I kind of alluded to, well, they're Cherenkov detectors that make use of this sort of flash of light that happens when a particle that is going faster than light would go in the medium that it's in. So water, for example, light goes 30% slower, 33% slower than it does, about 30% slower than it does in air. But a charged particle like an electron can still be going at the ordinary speed of light. And when something goes faster than the speed that ordinary light goes at in that material, you get this shock wave of light that's produced, which shows up as a little flash of a blue light or whatever. That's another kind of particle detector. Another kind is called the scintillation counter, that uses kind of an effect where, again, a charged particle going through can make electrons kind of move around in atoms and produce light. The end result is a flash of light. But all of those methods are capable of detecting muons. For some reason, scintillation counters are the most common thing that are actually used. Okay, what good does this do you? Well, you've got the source of muons from cosmic rays, and you've got kind of and they go into things like rock. And you can then have a detector on the other side of the rock, and you can say, well, how many muons got absorbed there? For example, is there a hole? Is there inside the rock? Is there a hole? Okay, so this got done for the Great Pyramid long ago. Somebody, who was it? Carter, and I'm forgetting. I forget who did this. I think this was done maybe 1940s, 1950s. I'm not sure. But in any case, what was done was to look at, there's a certain rate of muons that come from cosmic rays, and then you kind of detect how many muons come out when you're sort of at the side of the Great Pyramid. And that number, if the Great Pyramid is solid rock, then a certain number of muons will be absorbed. But if there's a great big kind of room inside the pyramid that's just empty, just has air in it, then not as many muons will be absorbed, because the rate of absorption of muons depends on the number of atoms that are there. And there are many fewer atoms in the gas in the air than there would be in the rock of the Great Pyramid. So that's a place where you can kind of, by looking at the amount of, you're kind of X-raying the Great Pyramid using muons. And in that case, most of the time the muons are getting absorbed, but some of the time there are muons that don't get absorbed. And that's and so that's a way to detect things like that. Well, okay, so muons, like other kinds of particles, the rate of absorption of muons depends on the atomic mass of a nucleus. So when you have heavier elements, it has you can have you'll have more absorption of muons. So if you're dealing with uranium with a atomic mass of 238, 235, that kind of size, there'll be lots of absorption of muons. When you have hydrogen or carbon or something, there'll be much less absorption of muons. Okay, so what? Well, so then you can start to use, you can basically use the sort of muons going through things as a way to do the analog of X-raying things like rock and you can tell things like, is there a heavy material, is there a heavy element, an element with high atomic number that's in this thing as opposed to not. So let's say you have a cargo container and you think it contains mostly, I don't know, bananas or something, which mostly have, hydrogen, oxygen, carbon, that kind of thing in them. I think bananas have a bunch of potassium in them as well. But I mean, I don't know whether it's significant. It's again a fairly light element. But if somebody had actually put a lump of uranium inside the shipping container, and in between the bananas, well, then it would absorb muons at a much higher rate. And so the idea is you can just, you have the shipping container, you put some particle detectors, and by knowing how many muons get absorbed in the shipping container, you can deduce, but it's sort of a way of X-raying in a sense, but not with X-rays, with muons, X-raying that container. Or for example, if you want to figure out, is there you're trying to work out, somewhere, is there a tunnel in this great pyramid, or is there a tunnel, somewhere underground or something? You can try and figure that out by detecting, are there muons that you would expect would have been absorbed in soil and so on, but there isn't any soil or isn't any rock there because there's actually a tunnel that's been carved out. And you can kind of deduce that by seeing the rate at which muons manage to make it through as opposed to being absorbed there. So that was a very long explanation. I thought this was going to be one of these really easy questions, but it involves quite a bit of physics to explain what's going on. But basically the idea is to use muons because they manage to go through material better than things like photons, you can sort of use them to do the analog of X-raying of things like rock. There are enough muons that come from cosmic rays, and they kind of are going fast enough, they last long enough that you can successfully detect them. And so that's how that works. Okay, that was a really long explanation. Sorry about that, the length of that. All right, let's try a few others here. I see JL is asking, how are elements created? Are they finite? Well, so chemical elements, hydrogen, helium, lithium, beryllium, etc., each successive element has one more proton in its nucleus. We know about on the order of 120 elements. The number of elements that are stable is about, 89, 90. As you make bigger and bigger nuclei, there is more of a chance that the nucleus will just fall apart. Confusingly, there are two elements that have comparatively few protons in the nucleus, but they are unstable: technetium and promethium. Technetium is element 43, promethium is element 60. Why are those unstable? Well, the explanations aren't really that clear, but roughly, the story is you can think of a nucleus as being like a bunch of spheres that represent the protons and neutrons all glommed together. And just like, you can see in a grocery store, there are these packings of spheres that you can get. Turns out if you have certain numbers of spheres, it's easier to pack them in a more compact way. If you have different numbers of spheres, they don't pack as well. And that's at least a qualitative explanation for why, strangely, elements 43 and 60 happen to be unstable. When you get to bigger elements, like when you're getting to radium and then uranium and so on, Those are just have a lot of protons and neutrons in their nucleus. They're sort of big and globulous, and they have a habit of falling apart. And by the time you get to the last element that's ever stable is uranium. And when you go beyond that, you're getting to elements where there is no stable isotope. There's no number of neutrons that makes it stable. And the nuclei, like by the time you're at 120 and things, the nuclei are falling apart in a, billion trillionth of a second. So very unstable. So nobody knows for sure that there won't be a nucleus that has a special, very careful arrangement of protons and neutrons that has, 130 or 140 protons or something that will miraculously somehow be stable. Nobody can say for sure that that won't happen. The state of figuring out how nuclear physics works just hasn't reached that point. It was long believed that there would be a so-called island of stability, where there are actually elements that are quite stable. Whether they will be absolutely stable or just fairly stable and only fall apart in a millionth of a second instead of a billion trillionth of a second wasn't clear. But it's still possible that that could be out there. Otherwise, what we observe is that as you just add in more protons and neutrons, things just fall apart instantly. So you might say, well, why can't you just make element 130? Well, you could take element 110 or something like this. You can just start, with a particle accelerator, you can start sort of throwing protons and neutrons at it. The problem is everything's just going to fall apart. It just doesn't, there's no moment at which you can say, yep, we've got everything all globbed together in a nucleus of element 130. By the time the protons arrived and the next protons arrived, the whole thing's fallen apart. So you can't really identify it as being a nucleus of any particular element. Now, there is a phenomenon where you can do that, and that's neutron stars. A neutron star is kind of like a great big nucleus with, 10 to the 50th, 10 to the 57, neutrons in it. It's like a giant, it's one giant atomic nucleus. It's maybe a few kilometers across. It has the same mass as the sun, roughly, or a bit more than the sun. And it's just a giant ball of neutrons. And that's, and the neutrons are bound together enough that they don't decay, and it just sits there. And the result of some supernova explosions is a neutron star, famously the Crab Nebula, formed in, when was it, 1054, I think, AD, has a neutron star at the center, and the neutron star rotates rapidly, and it produces a radio pulse. So it shows up as a pulsar that's producing regular radio pulses. That's a neutron star rapidly rotating on its axis. But so a neutron star is, in a sense, a very big, stable nucleus with an atomic number of like, 10 to the 57 or something. But that's kind of a weird case. For ordinary nuclei, there's by the time you get too many neutrons and protons in the nucleus, it's just going to fall apart immediately, and there'll never be a moment when it's all together. How are elements created? Well, the light elements were created in the early universe. So in the sufficiently early times in the Big Bang, there was sort of all possible particles, and they're all going around. It's all a very high temperature. There are quarks and there are gluons. There are all kinds of things like this. Eventually, by eventually I mean in a billionth of a second, or less actually, there are, you can sort of identify there as being protons there. And then after maybe a microsecond after the beginning of the universe, there start being the nuclei begin to form. Protons protons and neutrons that run into each other, they kind of glom together and they make atomic nuclei. And as the temperature goes down, when the temperature is too high, everything's running around too quickly. And every time, you might have formed a nucleus, but then some other thing will hit it and it will fly apart. But when the temperature is lower, there are things moving around less quickly, And so the sort of that stray proton, when it hits the little nucleus that's been formed, won't make it blow up. It might just add itself to it or something like that. But so after a microsecond after the beginning of the universe, millionth of a second after the beginning of the universe, the elements, the nuclei start forming. They get bigger and bigger. At the beginning, the only things that are there are protons and neutrons and other particles, but it's basically just protons and neutrons. But then the protons run into neutrons and they'll make two protons will run into each other. They'll make a helium nucleus, and it'll keep going. And these things just keep on sort of accumulating. More and more protons and neutrons and so on will run into each other, and they'll start making these elements. Okay, so the question is, how much of that happens before the universe has cooled down to the point where you can no longer sort of crash protons into little nuclei that have been made and have the protons stick? Because generally the nucleus will have positive charge, the protons have positive charge. You kind of, you send in a proton, it'll just bounce off. But if the proton has high enough energy, it can kind of get over the barrier that's needed, and it can get stuck with a strong nuclear force, and it can become a larger nucleus. But so a microsecond after the beginning of the universe, nuclei start to form. As time goes on, after that, within, I don't know, some limited number of microseconds, I think maybe a second, it's kind of the end of that epoch, and no more nuclei get formed. Whatever you've got is what you've got. Then, 100,000 years after the beginning of the universe, atoms form, and the protons and the electrons can kind of stably sort of hang out around protons, and they don't get bashed off by things running into them. And that's a significant time in the early history of the universe, because that's the time at which the universe becomes transparent to light, and that's the time from which the cosmic microwave background originates. That's kind of how far back we can see with visible light. With neutrinos, we could see a little bit further back. We can see back to, I think, a second after the beginning of the universe with neutrinos. But in any case, what happens is that in the first second or so of the universe, you've got a bunch of nuclei formed, and some nuclei get formed and others don't. So mostly in the universe, it's hydrogen. Most of the universe is hydrogen. About a quarter of what gets formed is helium, which is 2 protons, 2 neutrons, mostly. That's part of what happened during that violent period in the first second or so of the universe, that some of those protons ran into each other and made helium nuclei. Deuterium, the isotope of hydrogen that's a proton and a neutron, a small amount of that gets made in the early universe. But more elements get made as helium nuclei run into each other, and there's a certain amount that gets produced there. In stars, it's the same story, that you get, stars are mostly hydrogen, and then the hydrogen can fuse together, make somewhat heavier elements. It only gets as far as iron, iron 56. And the reason for that is, well, okay, this is going to get me into a whole other discussion. The reason for that is that the way the binding of protons and neutrons into nuclei works, when you kind of, if you stuff together, if you succeed in stuffing together protons and neutrons, then the resulting thing will have lower energy than the protons and neutrons on their own. And that's true from hydrogen up through iron. On the other side, iron to uranium and beyond, it's the other way around. You get sort of more energy, that things are, there's lower energy associated with things being apart than being together. Okay, what consequence does that have? That's why both nuclear fusion and nuclear fission can generate energy. So nuclear fusion is you ram atoms, nuclei together hard enough that they'll just stick. And that, when they're light nuclei with small numbers of protons and neutrons, the result of that is that the thing you get out has lower energy than the things you put in, and so energy is released. So that's how nuclear fusion works, and that's what's happening in the sun and so on, and in a hydrogen bomb. In nuclear fission, sort of an ordinary nuclear weapon, the other thing is happening, and instead you're breaking apart heavier elements and getting energy from that. And sort of the dividing line is at iron. So what happens is that the materials below iron can be formed in the early universe and in stars. Above iron, you don't get it in ordinary stars. The only way you get it is in supernovas, where there's sort of things are so violent that things are kind of being rammed into each other hard enough that you're even forming heavier elements. It's so-called, there are these different processes by which those are formed. The violent ones in the supernova, in the day or seconds of the supernova, rapid process nucleosynthesis, where you're just sort of ramming things together hard enough that you can kind of go past that sort of energetically favorable iron case, and you're getting heavier and heavier elements. So when we have a piece of gold, for example, atomic number 80, that we find on Earth, that gold must have come from a supernova. Our sun is certainly not a first generation star. It's and stars which become supernovas actually tend to last only a very short time, like a few million years. And so there's been many processings of supernovas that have exploded in our galaxy and in predecessors of our galaxy. And so when we see heavier elements, those are always coming from supernovas. And the material that formed the Earth, people say maybe there were like 5 supernovas that happened in the vicinity, and that's where most of the material that we see as heavy elements on the Earth came from. So that's kind of how that works. And by the way, the evidence that there isn't an island of stability and heavier elements beyond that element 130 or something that turns out to be stable, I suppose the main piece of evidence is, well, they weren't, we don't have any of them. But it could be the case that the physics of supernovas is such that it just doesn't quite get there. That in principle, you could make those things like in a particle accelerator or something, but supernovas don't quite manage it. It seems unlikely, but it's not impossible. And that would be an interesting thing if there was such a kind of island of stability, and there are all kinds of weird effects that will be associated with it. It could be a fascinating kind of material. I think it's very unlikely that it exists, but it's within the realm of possibility. And there are other kinds of effects that might exist. I mentioned that nuclei tend to be held together by the exchange of pions in the strong nuclear force. Well, there are other kinds of particles that get exchanged between protons and neutrons and so on. In addition to pions, there are things called rho particles, things called F mesons. Rho particles kind of are heavier than pions and kind of have an effect when you kind of stuff the protons closer together. And what happens is pions produce an attractive force, rho mesons produce a repulsive force. So when you push the protons even closer together, they'll start repelling each other. But then F mesons produce an attractive force again. They have an even higher mass. And so there's a possibility if you ram those protons together hard enough, maybe they would suddenly form this thing that's even more tightly bound, sort of micronucleus, so to speak. Nobody knows if that would happen. There's a little bit more evidence these days because a proton is, one often thinks of it as an indivisible thing, but actually it's a big fluffy thing at some scale. It's got a bunch of quarks and gluons. There are 3 primary quarks inside a proton, and there are gluons that are kind of holding those quarks together, particles that are being exchanged inside the proton. Well, so when you have a nucleus, it's like each proton is a bag of quarks and gluons, and they're sort of separate, but those protons are right up next to each other. And the extent to which you think of a nucleus as being a bunch of separated protons and neutrons, and the extent to which you think of it as kind of this big glob of quarks and gluons with just a slight sort of separation between them corresponding to these particles are not clear. And most likely the story with F mesons and so on is kind of going beyond the domain where you should think about them as separate protons and neutrons. And so that picture of saying, squash the nucleus hard enough, F mesons will start to get exchanged and the thing will be tightly bound. Probably that's not correct. Probably a good thing it's not correct, because you'd be able to make a sort of super nuclear weapon if it was possible to make kind of compressed nuclei that had this much higher binding energy. So in any case, probably those things don't exist, and probably the number of elements that are at all stable is the ones we know, and it's very finite. I mean, it has to be said, there are very weird effects that start happening when you have heavier elements. I'll just mention one of them. It's called autoionization. Here's what happens. So as the nucleus has positive electric charge, electrons have negative electric charge. Electrons are attracted to the nucleus. Normally, as the charge of the nucleus gets higher and higher, the electrons are kind of pulled in closer and closer to the nucleus. And that sort of keeps happening, and there's sort of more and more energy associated with that binding of the electrons towards the nucleus. Okay, at an atomic number of 137, something really weird happens. At that atomic number, the binding energy associated with the electrons being pulled in towards the nucleus is strong enough that it is enough that you can that binding energy can be traded off against making a whole nother particle. In particular, in an electron, there's an anti-electron, a positron, exactly the same as an electron, but with the opposite charge, a positive charge instead of a negative charge on the electron. Well, at d equals 137 atomic number, it turns out that in sort of fancy quantum mechanics terms, the lowest energy level associated with electrons gets pulled so far down that you can produce a positron by sort of just using that energy. So it's as if there's enough energy that's pulling that electron in towards the nucleus that you can kind of trade off that energy for producing a whole other particle. And so what happens is that the nucleus will start just spewing out electron-positron pairs. And what will actually happen is the nucleus will tend to shield itself by producing electrons that kind of get glommed into the nucleus, and positrons get ejected. But those electrons that are kind of glommed into the nucleus will reduce the effective charge of the nucleus because they're canceling out some of the proton electric charges. So in any case, that's one of the weird things that will happen. If you made it to an element 137, you would get the thing would start sort of having this weird kind of decay of autoionization, which there's some evidence that's been seen in the very, very temporary, heavy elements created in particle accelerators, where the thing lasts for, a trillionth of a second before it explodes. Okay, again, a long explanation. Let's see. Crystal is asking, would graphene be useful in neutrino detection? Maybe they're underestimating how small a neutrino is. Yeah, it's not really a question of size. Neutrinos interact with particles at they interact with quarks inside protons and neutrons. They interact with electrons. They just have a very weak rate of interaction. There's kind of a constant, a number that determines the rate of interaction, and it's very tiny. It happens to get multiplied by energy squared. So if the energy goes up, you can have a larger interaction. Now there's one footnote to this. It's a tricky thing. So when you have a big collection of atoms and you have something that comes in like it's a big, for example, you have a whole array of photons. You can think of that whole array of photons, it's a sort of a piece of electromagnetism, but you can think of it also as an electromagnetic wave. There's kind of these two complementary views of things like light, either a stream of photons or this kind of wave of electric and magnetic fields varying in time. Both of those they're both different views of the same kind of underlying sort of mathematical physics structure. But when you have this electromagnetic wave, it comes in and you've got these atoms and so on, and the electromagnetic wave hits this collection of atoms. The question is it the case that the different parts of that wave will interact what's called coherently with those different atoms? Or is it as if the different parts of those waves are really like different photons, and every photon is on its own, just interacting with whichever atom it happens to be near? Okay, so a little bit of mathy stuff. If there are n atoms when n is some number, like a billion atoms in this thing that you're interacting with, it turns out that if you have incoherent scattering, where every photon is sort of interacting on its own with an atom, then the rate of interaction is proportional just to the number of atoms, to n. But if you have coherent interaction, where this kind of whole wave is kind of coherently and sort of collectively interacting with those atoms, the rate of interaction is like n squared. So coherent scattering, which is what happens when you have, for example, when you detect a radio wave, you're using coherent scattering. You're using the fact that the radio wave is kind of wiggling all those electrons together, and together they produce an effect that is like the square of the number of electrons. Okay, well, what happens with neutrinos? So can neutrinos have coherent scattering, or must neutrinos always be one neutrino, one atom type scattering, incoherent scattering? Good question. So back in, when was it? 1983, 84 or so. For one brief moment, I thought there was a way to get coherent neutrino scattering. So one feature of neutrinos is they affect the spin of particles. So, okay, tricky fact about neutrinos. So an electron, for example, it can be spinning one way or it can be spinning the other way. Let's say you have an electron, it's like a little top. At least you can think of it as like a little top, and the top can either be spinning with the axis of the top pointing up, or it can be spinning counterclockwise, or whatever the axis of the top pointing down. And in quantum mechanics, one sort of makes this distinction of spin up, spin down. Those are two sort of things one can distinguish. It can also be spinning in different directions, but you sort of separate out those two cases. Okay, so an electron can have either spin up or spin down. It can be either left-handed, spinning sort of so that if it's going on let's see, if it's going in the direction of one's thumb, it can either have a sort of a spin that's aligned with one's fingers, or it can be right-handed, going in the direction of one's thumb, aligning with one's right-hand fingers. So electrons, both things are possible. Okay, neutrinos. Strange fact about neutrinos, basically every neutrino is left-handed. Every neutrino has a spin that is essentially anti-aligned with its direction of motion. Every antineutrino is right-handed, has a spin that is essentially aligned with the direction of motion. There's tiny variations from that to do with the tiny mass of neutrinos, but that's a good first approximation. So when you have this the spin thing, and by the way, that kind of goes against what you would usually think of as coherent scattering, because spin is a property of individual atoms, individual particles, individual nuclei, whatever. And so you can always know if a neutrino hit one particular atom and it flipped its spin, you can always know that by just looking at the spins of the atoms. It's not something where you get sort of confused between all the possible atoms. Okay, there is a particular material, superfluid helium-3, the A phase of helium-3, that has the feature that it has large-scale aligned spins. And it's, okay, so helium, okay, so most materials, when you cool them down far enough, eventually the atoms kind of stop jiggling around, and you no longer have a liquid where the atoms can jiggle around. You have to have a solid where all the atoms are kind of locked in place. Usually, as you go to the absolute zero of temperature, minus 273 degrees centigrade, roughly, you'll end up with a solid. The one exception to that is helium. Helium, there is enough kind of quantum mechanical jiggling that happens even at absolute zero that helium is still liquid at absolute zero at ordinary pressure. Helium-3 has a oh gosh, this is complicated. Okay, there's another phenomenon called superfluidity, and here's roughly how that works. Normally in a liquid, for example, the atoms of the liquid are jiggling around randomly, but there's in certain cases, when the temperature goes down, roughly what happens is when the temperature goes low enough, in a solid, all the atoms are kind of locked in place. There is also the possibility of a superfluid where the atoms are not locked in place, but they tend to move together. So, for example, in an ordinary fluid, there's viscosity. If you start sort of moving something through the fluid, there'll be kind of friction, and that motion will be turned into microscopic motion of molecules, and you'll come to rest. If you're just a thing that's going through water, there'll be a lot of kind of effectively friction from the water that makes you, that has resistance to motion. In superfluids, there isn't that. In superfluids, even though the molecules are still able to move around like in a liquid, they all move around in a giant sort of platoon. They all move together. And that phenomenon happens in some materials. It happens in helium. Whether that phenomenon happens depends on the detailed properties of the nuclei of atoms. There are two different kinds, so-called fermions and bosons, that are distinguished by the spin of the particles. It's again, ask me about it some other time. There's a connection between spin and statistics. Things with half-integer spin, like electrons and protons, are fermions. Things with integer spin, like photons, are bosons. And bosons like to get together in the same state and all move together. Fermions like to avoid each other and stay out of each other's states, so to speak. So the way lasers work is they are the result of kind of the condensation of bosons, photons, into the same state that causes sort of all the light that comes out of a laser to sort of all move in the same way, be the same. And that's sort of how lasers work. Superfluidity is the same kind of idea, but it happens with atoms. And whether you can get it with atoms depends on the on whether they have integer spin or not. Helium-4 has an integer spin. Protons and neutrons each have half integer spin, but 4 of them together has integer spin. Helium-3 has half integer spin, but just to be complicated, you can get pairings up of half integer spin things that act as integer spin things. Anyway, this happens in the A phase of helium-3. You get pairings up of these nuclei, and they pair up together to make a spin 1 object. So each individual one is spin a half, they pair up to spin 1, and that means there is a net spin, but it is still an integer, so you get superfluidity. So the end result is, in superfluid helium-3, the so-called A phase of superfluid helium-3, you can have a situation where you have all of these nuclear spins all lined up in the material, and the result is that you have sort of a net spin to the thing. So the question is, if you have a neutrino that's coming in and it's going to flip the spin, could it flip that whole spin coherently of a big lump of superfluid helium-3? That was the thing that I wondered back in 1983, 1984. And okay, so what if it could do that? Well, the so what is that then you could have coherent scattering of neutrinos, and instead of there being a factor of n for the amount of interaction, there'd be a factor n squared. And with a big lump of helium-3, that n squared could be big enough that you would be able to make a detector of neutrinos. And so the statement that I made earlier, that it's really hard to detect a neutrino because most things just go straight through, if you could make it do coherent scattering, then it would not go straight through. It would coherently scatter, and you'd be able to measure the effect. So that would have been a cool effect, that you could detect neutrinos. The only problem was, right at that moment in world history was kind of an awkward time to be detecting neutrinos, because nuclear reactors produce neutrinos. They produce isotopes that undergo beta decay, and they spew out neutrinos. And well, where are their nuclear reactors? Well, they're nuclear reactors for nuclear power and power plants and things. They're also nuclear reactors on nuclear submarines. And at that time, particularly in the Cold War, a big sort of piece of the story was, oh, the US and the Soviet Union and some other countries have a bunch of nuclear submarines tooling around deep under the ocean, and nobody knows where they are. And if everything falls apart, well, there'll be a nuclear submarine that won't be destroyed, and it will be able to fight back. Well, that all works fine so long as you don't know where the nuclear submarines are. But the problem is each nuclear submarine is spewing out neutrinos. If you don't know where the neutrinos are, you don't know where the nuclear submarine is, and all's good. But if you could detect neutrinos easily, then you would immediately know where all the nuclear submarines are. And if you're using the nuclear submarines as a sort of last resort kind of story, that gets blown up immediately. So the question was, if you could detect neutrinos from a nuclear reactor, from a nuclear submarine, for example, from something in orbit, could you, in one fell swoop, basically just make a map of where all the nuclear submarines are? So the question was, if you know how to do that, what do you do with that information? Because it's a very awkward thing to it's kind of an awkward thing in the world. So I was kind of agonizing about that for a few days as I was trying to work out properties of superfluid helium-3 and neutrino interactions with it and so on. And it was one of those cases where, often you hope that these weird science effects actually work out and you can tell something interesting. But in that particular case, I was really happy it didn't work out. It isn't possible, so far as I could tell, to make that particular scheme for neutrino interaction work. So it was really good because I was trying to figure out what on earth do you do with this information? Because as soon as that information is out there, sort of even the fact that everybody knows that in principle you can detect where the nuclear submarines are has all kinds of problems associated with it. And as I say, I was just about figuring out here's how I tell, who I tell, what I do, et cetera, et cetera, et cetera, when I was like, let me check this some more. And I'm like, it's not going to work. Great. Let's see. All right, I think I have to go back to my day job here. Mean is asking, let me just look at a few other things which are questions related to the specific topics that I was talking about here. But by the way, this question from Crystal about graphene and neutrino detection. Graphene has, I don't think the effect of coherent scattering, I don't think anything can make that work. But there are certainly strange electronic properties of things like graphene that one might look at for that, but I don't think it won't work, happily. Let's see, Mean is asking, if a chunk of neutron star fell off, then do all the neutrons fly off? No, they don't. A neutron star actually, strangely enough, neutron stars are superfluids. The neutrons in them, it's very weird. Neutron stars are very weird things. I mean, it's mostly this kind of, this strange state of matter that's just a bunch of neutrons that behave as a superfluid, probably, but the crust of a neutron star is iron 56. There's a thin layer of iron on the surface of a neutron star, just because of the way that the energetics of nuclei work. And probably inside a neutron star, there are some places where they're really just quarks and gluons. And probably, just to be exotic, there are probably strange particles. Those are things, ordinary, like protons and neutrons contain up quarks and down quarks. But there are 4 other kinds of quarks that are known that have higher mass and are unstable. There's strange quarks, which are, and strange quarks make so-called strange particles, of which, well, I don't know whether any of them are famous. They should be. These the kinds of particles were certainly my personal friends when I was a kid. Just to mention them, just as a name check some particles, the lambda hyperon. Let's see, a proton has a mass of 938 MeV. Those are just the units of million mega electron volts. They're just the units one usually uses to measure particle masses. So proton 938, neutron I think 939. That's why a neutron gets to be unstable, because it has a mass a little bit higher than the proton. Electron has a mass of about half an MeV. Then the lambda particle, which has a strange quark, an up quark, a down quark, and a strange quark. A proton has an up quark, and a down quark. The lambda hyperon has a mass of 1115 MeV, and it's unstable. It decays into a proton and a pion, but it has that's one form of strange particle. There are also the sigma hyperons. I think they have a mass of, this is really testing see whether these neurons are still alive. I knew this stuff well when I was an early teenager. I think 1385 MeV. Somebody can check that. You can type it into Wolfram Alpha and see if I'm right. I think that's the mass of the 3 sigma particles. And then there are some more exotic ones. Those particles, the lambdas, the sigmas, have strangeness 1. And then there are the psi particles, the cascade hyperons. I think their mass is, boy, this is really testing my memory. 1400, I think, that order, maybe 1450, something like that. They have strangeness 2. And then a particle which was actually predicted before it was discovered, the omega minus, has strangeness 3. It's again has slightly higher mass, 1875 MeV, something like that. Those are strange particles that decay quite rapidly into ordinary particles, actually through this weak interaction that I've been talking about. There are also the pion as a kind of an ordinary thing. It's an up quark and an anti-down quark and various combinations of that. There are also strange particles like that. The kaon, a strange quark and an anti-down quark, for example, is a kaon. That's another particle that decays rapidly into pions. In any case, there are these so-called strange particles, which in the normal course of kind of matter on Earth, there aren't any strange particles because their lifetimes are on the order of 100 millionth of a second or less. But in a neutron star, because the kind of situation is rather different, you can get strange particles just sort of hanging out inside a neutron star, at least probably. And there are kind of neutron star quakes, and maybe some of those are associated with kind of the change from it's all neutrons to there's some strange particles there to other kinds of phenomena like that. So neutron stars can do wild things. But a neutron star is pretty tightly bound together, and it's a pretty close to perfect sphere because it's got sort of gravitational forces. Just to be clear, a neutron star has the density of an atomic nucleus. So an atomic nucleus has a density of 100 trillion times the density of water. So water is 1 gram per cc. An atomic nucleus is 10 to the 14 grams per cc. So atomic nucleus is extremely dense. That's the same density as a neutron star. And it's not surprising that it has to be that density because a neutron star is formed from a star a bit more massive than the sun, kind of collapsing on itself. And you've got to get the whole mass of a star into something which in the end is a few kilometers across. And so it's not surprising that it has very high density, but it really is like a giant atomic nucleus with that density. And that density is so high, and the kind of the forces of the thing are such that it really ends up being within microns, an absolutely perfect sphere. And so any kind of surface imperfection is very rapidly sort of pulled down by gravity, and it can't be kind of resisted by the kind of forces inside the object. So really, pieces of neutron stars do not fall off. There are occasionally neutron star mergers where 2 neutron stars very close together and eventually run into each other and merge. I don't know for sure whether gravitational waves from neutron star mergers have yet been observed. Most gravitational waves that are observed are from black hole mergers that are a bit more violent than neutron star mergers, and I don't know exactly what's known about that. I mean, roughly what's going to happen is you've got these 2 spherical neutron stars, and they're going to merge, and they'll make this kind of single spherical thing, but it'll blob around for a while, kind of ringing like a bell, and producing all kinds of gravitational waves in that process. But I know that's something that should be observable with gravitational wave detectors, either real soon or has already been observed. I'm not sure. All right. Let's see. All right. I think I can. There's more questions here that are real interesting, but I've got to go to my day job and make sure that the next version of our product actually gets finished and is great. So thanks for joining me, and see you another time. Bye for now.